Okay, Friday afternoon, time for Token Drop. And this week we have a special guest, Raminda Madurawe. He's a founder and CEO of AxPro Semi. Raminda I've known for a long time and one of the most sharpest technical folks I know in the chip world. And today we're going to talk a little bit about the whole trends kicked off by Cerebras. And I thought, who else to talk about that than Raminda? Because I'm sure he'll have some interesting ideas on that. So Raminda, we usually chat maybe 20, 30 minutes on a topic of interest to us. And this week we decided, hey, let's talk about what Cerebras means more broadly. We tend not to talk about a specific company. We don't talk about our products. We just talk in generalities. So let's get going. So, Cerebras had the IPO. And you know who's over there, Sajad? I don't know if you remember her, Julie Choi. And she was at Intel, and we worked with her on the press release we did back at our Wipro days.
Yeah.
And I think she went over to Raminda Madaurawe's company. And then when that company got purchased by Databricks, I think she ended up as a chief marketing person at Cerebras. So I haven't talked to her in many years. I'll just wish her congratulations on her IPO. Tremendous IPO, right? And it's done very well. So what we can probably talk about is, does this herald, what impact does it have for the AI industry more broadly? Right. So they have their chips and you can buy their systems, you can use their cloud. Is that what we're going to see more of people building their chips, and then individual corporations can use those chips if they want, or they can use the chips in terms of an application layer to call it via an API, so that they don't have to worry about doing anything at the chip layer. That's the responsibility of the company. And people like us could just use it from an API perspective, right? We, for example, might use Claude or OpenAI today in our applications, and we do that via an API layer. So it doesn't matter to us if it's on AWS or Azure, what they're doing behind the scenes, how they're executing those LLM commands. It just works. And is that what we're going to see more of, where the cloud guys are saying, hey, I'm going to now run this on Cerebras or whatever, or what are we going to see? So maybe we'll throw it open for you, Raminda, as our guest. What do you think?
So I can share. First, thank you for asking me to join your chat. So coming back, the point that you raise is well taken. If you have an API and the API can run anywhere in platform X, Y, or Z, the guy who does the API doesn't care whether you ran it on X, Y, or Z. You'll find what is the most optimal, either cost point, power point, whatever the metric you want to do, and you'll run it. But then comes the hardware side. On the hardware side, the question that we've all tried to answer is, can you run any API transparently? Or do I have to pay a tax to run your API on my hardware? And the answer is all the time, you have to pay a tax to run your API on my hardware. And then the question is, what is the tax and in what form do you pay for it? So there is a software related tax you have to pay. That means you may run your API, but I have to convert that software into additional software I need for your API to run. The second is there's always an indirection tax. That means my silicon is not very efficient to run your API, but I will run it at some inefficiency. And so there is overhead related to that. And the third one is, I may not be able to get the same power and the accuracy you desire. So I have some kind of a, let's call it an accuracy or utilization or an efficiency tax. So these are the three variables that we always try to optimize. And I think today you want to specifically look at Cerebras.
And just in general, in general. Yeah.
Or you can even speak in terms of that architectural paradigm. In architecture. So if you go back to a CPU architecture, then because of all the accelerators that have come in to do AI, just a CPU architecture was never good enough to do AI workloads. So you can say, I need to have some kind of an AI accelerator architecture if I want to do the type of workload that AI has to do. So then you can ask the question, supposing a CPU could have done an AI workload, would you have still done an accelerator? And nobody knows the answer. But the chances are you probably didn't need to, because nobody would have even bothered to do an accelerator, but it doesn't matter. Today we have to do the accelerator, right? Everybody did a GPU type of architecture because it was built for some other purpose and it was available and it was a nice backup to piggyback your AI workload because it was able to handle what the CPU couldn't handle. So then automatically you ask the question, gee, is there a different kind of architecture that would have mattered? And then that answer comes in a mathematical question, which is, what is the data graph you want to compute for your mathematical function? GPUs build a certain type of a data graph. Then you ask, can I build a more efficient data graph that can do it in quicker, better, lower power, whatever the metric you want to throw, right? So we can go that path because there's a lot of thought going across in that phase. But there's a parallel question to ask, and that is, if you want the computing at the most efficient, the performance power point of operation, what is that piece of hardware? And the answer is a custom ASIC that does exactly that function you want to do. Nothing is more efficient compared to that piece of silicon. But you have a flexibility tax because you might need 20 different things to do. So what are you going to do? 20, 30, 40? What's the number? Pieces of ASICs you're going to put. So then that becomes an overhead tax to use one. You cannot pay for 20, 30 of those choices. So, but the world, to your point, Sunil, is coming with these domain-specific accelerators, hoping that a larger group of applications will use that piece of silicon, thereby amortizing the cost of it, and it'll be more appealing to a larger group of people. So on the one side, you have the GPUs and the NPUs that say, we'll give you an instruction set and give you a smaller set of functions that you can use through instructions to get a better accelerated computing. Then there's another group of people that said, no, no, no. I will build you a large data graph. You will need a large amount of silicon. Now you can parallelly process a large compute graph and get a much better throughput because you are throwing a lot of silicon at this, right? So two different thought processes have gone a great extent. You see many companies that are doing these large silicon footprint solutions, and there's this other form of accelerated form of computing solutions. And when you go to the cloud, your question gets a little bit different, and that is, since you have so many users, can I share my silicon or my hardware across multiple users? How do I divide the time each user uses this piece of silicon? And if more users can use the same exact model, then I don't have to load a lot of different types of model parameters. I can only use the user-specific content and perhaps get an advantage, right? So in this world, we have come across all these different solutions that we see today. And you ask the question, where would it end? And I have always felt the cloud is really good when you want to look at what is everybody else doing, how can I find what they are doing, How can I summarize what they are doing? And I do it all the time. You guys do it all the time. But the next piece of it is, why do I do that? Sometimes it's to find a restaurant. I don't care, right? But when it comes to work-related work, by the way, we use AI very heavily in my company, and I'm sure you guys use AI very heavily. I really don't want to put my information out in the cloud for anybody else to learn from whatever I'm learning. So I want it to my private data, and I can't do that today. So I'm kind of restricted in how I applied it, and the rest of it, we do it at home. And I keep thinking, wouldn't it be nice if every computer is a data center? Wouldn't you want your own stuff to be done locally at your own pace? And why do we need a model that tells you, what somebody in London is doing with somebody else, which you don't care? Wouldn't you rather just, for your own folks, have a little bit more custom but more accurate system without any hallucination? So this world, I think, is my feeling is that it is going to get divided into these two, and we see that coming. You see a lot of AI PCs coming into the marketplace. But if you look at the specs and the marketing, there are two different things, right? There's a reality and there's a hype in marketing that you try to cloud what is reality. So in the cloud, any model you want to run today, OpenAI, anything, they're using FP16 precision, and arguably it's because if you don't do it, you're going to lose some accuracy or some level of uncertainty that you don't want to give up. Otherwise, everybody would have used a lower quantization because it's a lot less in power. But an AI PC, you will read, oh, 4-bit quantization is good enough. So why, if it's good enough for your PC, wasn't it good enough for the cloud? I don't know the answer. So I'm assuming there's a lot of marketing behind if P4 is good enough, or you are being told compromise your accuracy, certainty, because you are using a cheap solution. So you be happy with it. If you want better accuracy, come to a more expensive solution up in the cloud, pay for it, and you'll get it, right?
So maybe this is a good time to maybe break, Raminda, and ask what these other guys think.
Okay, sorry. Yeah, go ahead.
No worries. I think
now you throw it open and ask questions, and we can go from there.
Yeah, thanks for setting the stage. I think the trade-offs and the design choices, and why would you run on a PC and why not run it on the cloud or vice versa? And it could also be the case that as a service provider, I might want to provide the largest diversity of models, and some of them are really, really large models, and some might be small models. And how do I serve them efficiently? And this is a problem we have struggled with, and the choice comes down to find the most popular models, host them, and serve them, and then there's a long tail of models. You can offer some other APIs to customers so that they can spin up such models on the device and then run them. So you don't need to continuously run such models on your own. But if somebody were to come along and say, I need that model on this device, and you can say, here's the API to make it happen, go do it.
Yeah.
But given this wafer scale computing paradigm we're talking about, and I assume the integration and the number of transistors is only going to increase. So the question for you is, and is anyone even talking about it today, on such a large estate, can I partition that estate and run diversity of different models? Some are big, some are small, on the same wafer, and serve multiple different applications?
So I think the short answer to that question, it should be possible. And because if you take a wafer scale integrated model, they all have some kind of a control layer that is able to run some control features across a certain diversity of space. because it's divided by space. So in that argument, you could technically partition it into quadrants if you can feed the required data in that fashion, but it needs to be architected to feed the data. Because even in a wafer scale integration, these large language models, like 1 trillion parameters, will never fit.
Yeah.
So you break it down into a single layer. Even a single layer might sometimes exceed what you need in the wafer. Now you're asking the question, what happens if it's only a quarter of that? And then can I use 4 of those models in parallel? And then it has to be architected to be divided. And that's a hardware decision you have to make upfront. Because if you don't make that decision, then you can't feed it, because when you feed data into the wafer, there's some kind of a bus wafer feed technique, right? So through the bus, you get it, and then you should be able to distribute it into the quadrant. So if that technique doesn't exist, then you can't. And quite a lot of these wafer scale architectures, Sajat, they have a flat memory architecture, which suggests that they don't necessarily partition the memory into quadrants and load it, right? They just go through some kind of a systematic way of loading it into each of these memory blocks, and they process through that.
Yeah, in the case of Cerebras, they have these cells, and it's a network of these cells, and each cell has some compute, it has a router, and it has some memory. I was a little intrigued by the fact that when you have such a large die, and still you have such a less amount of memory on it, it's like it runs into tens of gigabytes, which is not very different from an NVIDIA GPU, a high-end NVIDIA GPU. So, although in high-end NVIDIA GPU, you are using HBMs and you're using, it's not SRAM directly on the die, but it is on the side that you connect with. Yeah. So what still perplexed me was that the amount of memory you have, SRAM, on this wafer scale chip was still running into tens of gigabytes. It wasn't like hundreds of gigabytes.
It was about 44 gig, right? On
yeah. So from SRAM perspective, 44 gigabytes is a heck of a lot.
Yeah. Right.
But compared to DRAM, it's like one chip of DRAM is 32 gigabytes. So what's the big deal here, right? So,
oh yes, right. Thanks for pointing that out. This is the difference between SRAM and DRAM.
Yeah, so that's what you're referring to.
Yeah.
So that's a question I asked about 2-3 years ago when we were trying to do our company. And it boils down to, first, the DRAM bit cell itself is quite a bit smaller than an SRAM bit cell. But that's not the primary factor. The primary factor is the DRAM guys know how to build skyscrapers. So in a small footprint, they can put a lot of these layers and offer you, 32 gigabytes in a single chip, which is, if I'm not mistaken, about 190 millimeters squared can give you 32 gigabytes of DRAM data.
Right.
SRAM bit cell is to begin with 4 or 5 times bigger per bit cell, and there is no technology to put one on top of the other and give them. So you have to occupy real estate.
Yep.
So this real estate in anything is so expensive. And the other thing is SRAM cells, Sajat and Sam, they don't scale with technology anymore.
Yep.
You can go to a 3 nanometer, 2 nanometer, 5 nanometer. The bit cell is almost the same size.
This is about 7 nanometers, right? I mean,
so 7 nanometer bit cell may be just a tad bigger than a 3 nanometer. So there is really no big advantage in going to a smaller, even though you have a power savings performance on logic, you don't really get that much on SRAM, right? So you asked the question, so what is a better model? Do you want SRAM sitting as a real estate and move the data from house to house to house to house because every house has SRAM? Or do you want to operate within a house bring your data to the house, do your operation, bring the next set of model parameters to the same house, do the operation. In the second, you need less real estate, but more power. And your efficiency may be less because you have to wait for all these things to arrive too, right? It's not waiting for them.
When you're talking about this, specifically, I had a question about GPUs, right? In the tensor processing units. Now
Yes.
they shunt that across the data to the tensor processing units because that specialized process, right? Now you have the movement there. So how do you come? So here, what I'm trying to get at is basically you're talking about the main thing, right? That the paradigm that these guys are talking about is the fact that memory bandwidth, not compute, is the real bottleneck in AI workloads. So they put all the memory on the single piece of silicon as the compute and make that piece of silicon as large as physics allows. I mean, this is what I understood. Correct me if I'm wrong.
Yes.
Yeah.
So thank you for that point, because there's two things that I've tried to figure out and get an answer to, and that is, what exactly do you mean by memory bandwidth and what exactly do you mean by compute bandwidth? And in that answer, a CPU typically gets data from a cache memory. And in a CPU, the caches are designed knowing that you have an instruction cache and a data cache. And the data cache needs operands. And these are either some finite small number of bytes. They're never SIMD because you are doing general purpose, right? So it's a small pipeline. Therefore, you can only read the operands of a small data size. So you call it a data bandwidth limit because you cannot get more than that. The CPU cannot use it anyway. GPUs have a little bit more flexibility because now they can give you a SIMD instruction. And by definition, they can design it to a bigger bus width or a bigger bandwidth. So each operation, an instruction, can do 128 bytes of data, some larger number, all in parallel, so you get a bigger bandwidth. Even then, GPUs run into a memory bandwidth because that data has to come from an outside memory through another bus, not the chip bus, but an external bus. So they are playing a lot of games on how do you increase that bandwidth, and everybody would be familiar with HBMs. HBMs are increasing the bus width from a 64 bus wire bus of a DDR into the HBM, which is going to expand to 2048 pins when they go to the next generation of HBM4 or something like that, right? So now you have to balance what you get from outside and feed it inside the chip. So it's not limited to just one of them.
Yeah.
And the CPUs have a problem distributing it. On the one side, you have to feed it to a CPU. You have to feed it to an NPU. So you have to feed it to disparate computing, and your wires and wire meshes, you can't have two different architectures. GPUs have one architecture, so they also have a limitation on that, right? So I'm assuming that based on the data rate, Cerebras and the likes, because they have so much more memory inside the die, once they load a die, the entire wafer, so many die, they can process that much of memory very quickly because now it's on chip, not on one chip, on 72 different chips of a single wafer. So it's basically 72 chips worth of parallel processing.
Yeah.
But I would think they also have the issue of after you finish that data, what about the next set of data?
Exactly.
Now you have to bring it from outside. So it's a matter of how you divide and conquer this game. And I'm sure in some areas you win and in some areas you don't win, right?
It's around huge, right? It's about
you can't do both.
The memory bandwidth seems to be about 21 petabytes. That's what I'm looking at, actually. And again, you brought a very interesting point about the model, right? because even if you take, say, an Emetron 253B or any huge model, you have to go with basically sharding. So naturally, the GPUs have to be connected. So you in a typical setup, it's about 8 GPUs actually, 8 H100 say connected through an NVLink. And now you have to do all kinds of operations between these GPUs, like all reduce operations, stuff like that. Now that is gone with this approach with Cerebras is using, right? I mean, basically, there's no interchip networking for the model itself, actually. That's one of their claims, right? I mean, as they see,
Yes.
and they even solve the yield problem at a different level, actually. So I want you to, because you are an expert and I wanted to hear from you.
Yeah, so thank you. So that's this NVLink is a really nice concept. So if you don't mind, I'll give a bit of a history on that. This is my extraction, trying to get at it. We all use a PCIe link to do communication. Unfortunately, every time you want to get on the bus, there's a penalty of so many microseconds before you can get on the bus and go to communicate, because it's shared by many different things connected to it. NVLink is a little bit more point-to-point connection. It can give you a latency a little bit better than a PCIe. Apparently, you can get about 4 microsecond latency compared to the 10, so you have an advantage. But they still use a 64-wire bus with PAM4 kind of data compression to transfer between 2 different domains. And when I looked at the recent GPU connected to a CPU through an NVLink, in some of these high performance super chips, they get a data rate of something in the order of 900 gigabytes per second. And that is between a 72-core CPU engine and some roughly 70, 80 cluster GPU chip connected with this massive bus. And the same connectivity can go from, you just mentioned, one GPU to another GPU to another GPU. So every time you want to communicate between the two or access virtual memory that is along this NVLink, you still have to access the NVLink. You have to, all the CPU calls have to go through this NVLink. So there is a latency and a penalty that they have to pay for communication between a single CPU core and a single GPU core, because that link is the connection. Clearly, a wafer scale engine sitting right next to each other doesn't have this link. I would expect that they can do a much better job in this interaction and get a performance advantage, perhaps a power advantage as well, right? And this is a fundamental difficulty for a GPU CPU architecture, because you have to have 2 different chips doing it. You can probably put it on the same chip next to each other and get a link in. Then the GPU efficiency may be diminished because the CPU and the GPU may not be together, right? That's for somebody else to think of. A nicer approach is if there was a fancy way where you can actually integrate all that activity inside a single CPU core, so that you don't have that latency, you don't have the bandwidth penalty, you can the interoperability significantly improves, then all that efficiency will be yours for you to have, right? So that there is a future possibility that could happen and make out. The part I don't like throwing a lot of silicon, Sunil, is, I mean, when we were doing chips in our younger days, right? The whole goal was to come up with the smallest piece of silicon you possibly could.
Yeah, absolutely.
And so now it is, geez, how many of these things can we build? How big can it be?
Yeah, exactly.
And suddenly you are saying it's not a local solution anymore. You are saying this is a centralized solution who can hold these massive things. What is the power, Sajad? It's 20 kilowatts for one of these single wafers, right? Some of these GPU racks are 120 kilowatts.
Yeah.
There's got to be some
cooled.
number. Miss Eggy, kilowatts? Oh my God, really?
Yes, it's
It's not
20 kilowatts.
not 20 watts, huh?
It's a power spec for this.
Geez.
It's not 500 kilowatts, I think, actually. Fits in 1/3 of a standard data center rack.
So it's all liquid cooled, and there are these fancy fins. And you have all these new companies. And I was talking to a cooling company, and I said, the best cooling solution you can have is not to have cooling. Right? Because anything else is you're trying to solve somebody else's problem that they should not have created in the first place. So,
actually, Sajad alluded to this. I just wanted to bring this question into you. Like the HBM bandwidth, right? About approximately 3 terabytes in the case of a H100, right? I mean, or about 8 terabytes on the B200 is a ceiling, right? On Cerebras, the weights sit in the SRAM you're talking about, in SRAM nanometers from the computer. It's in nanometers from the computer, right? I mean, so they are able to get that 21 petabytes per second and single cycle access, right? What's your thought on that? I mean,
yes.
Is this the entire reason Cerebras destroys the GPU on token generation speed?
Yes. Thank you for that. Because there's a lot of people, there's an interesting point that you raised, and that is when you operate out of cache, what is the total bandwidth of that operation in teraops? And you will get, even for a 72-core CPU operating at 4 gigahertz, you will get a large number. This is why NPUs, a 6 or 8 cores of NPU, will give you 48 terabytes. The Apple M4 will give you 48. It's approximately in that number of ballpark. It will be able to operate for about 100 cycles. After that, the cache is flushed. And now you have to wait to refill the cache. So just imagine, instead of 8 cores, if they build an entire wafer full of cores. These 8 cores are about 2 or 4 millimeters squared in area. Supposing you expand it to 40,000 millimeters squared, which is the size of a Cerebras solution. Can you imagine 48 divide by 2 multiply 40,000? How many petaflops that would be, right? It would be huge. So this number of petaflops after 40,000, if you do the math, is, yes, it's a large number. But if you scale an NPU to a similar area, you will get like orders of magnitude bigger number, right? So, but the real issue is it is running out of a local memory. How long would it take for you to fill the local memory?
Speaking of
because eventually it's a two-pong game, right? It's not a single number.
That brings me to another interesting architectural question. Right? We're still speaking classical von Neumann architectures, right?
Yes.
So now what about data flow architectures? When you have, let's say, a wafer scale engine, which has local SRAM and local compute, and they're all interconnected. So you have the weights and the model code distributed across this wafer scale. And you have inference data just flowing through it. And as inference data reaches each unit, it's processed and forwarded on. And you have a pipeline of those data flows. So in some sense, it'll resemble a data flow architecture. And there's one company that has done that. I think Sambanova tried building that. I don't know where they are with it. But what are your thoughts on Sambanova versus Cerebras versus the true definition of data?
Okay, I'm glad you just picked those two because I've actually spent a bit of time looking at both of those.
Okay.
I don't do it for all of them. So
Raminda, one question, right?
Yeah.
I mean, I want you to also talk about Grok LPU compared to Sambanova's reconfigurable.
Grok, I've looked at about couple of 2-3 years ago, so my
Yeah.
memory may
I
not be
wanted to
as
yeah,
good on
make
that
the
one.
comparison.
But
Yes.
Sam, maybe just for the sake of time, we
But
can
I
ask
will
him
give you
those two.
the good and the bad as I see, right?
Okay.
So Sajad, on the Cerebras application, they still run a custom instruction processing unit. It's a small instruction set. They are able to loop and execute within that instruction capability, but they seem to be able to provide an asynchronous computing technique, and they've shoved the ability to make it asynchronous into metadata of a data packet. So that decides the triggering of the next activity. So you increase the data packet, you provide some overhead, and that data packet, once it's done, can then decide how do I move to the next or anything else, right? So, and being asynchronous, you can always get a efficiency improvement over synchronous because you don't have to wait and make sure that everything is aligned. GPUs are synchronous.
Yeah.
You have to make sure that all of the things, so they're correct, I think, in their statement that they can get a little bit more efficiency through this technique. But they are not a perfect systolic data graph. On the other hand, SambaNova is a complete systolic data graph. So now what's the good and what's the bad? So when you have a complete systolic data graph and the model parameters are frozen into the data graph, so there is no feed in from anywhere else, let's assume that as a constraint, then the user's attention data or the KV cache for the user has to come in, and now everything has to flow all the way through the engine to the very end, right? And that KV cache depends on your context.
Yeah.
You will have one, he will have another, third person will have another. So your partitioning and the data graph is a user-defined variable. You can't have a user-defined variable being a data graph and fit it for everybody. Right? So you have to quantize a data graph and say anybody with less than 100 tokens, I will use this. If it's more, I reconfigure it, and then you have to use this second one. Because if you try to bring model data again and again, you've lost your advantage in the first place.
Yeah.
Because the advantage is you have the data on chip, right? So the advantage is the fact that you don't have to load memory data. So SambaNova doesn't need to, but Cerebras does. So because they only program one layer at a time. So then when the next layer comes, you have to program the next layer. And if the layer was too big, they probably have to do it in 2 batches. I don't know, some game they will have to play, right? So Grok is also similar in the sense that they also try to build this data graph, and they do it. Then comes the fixed content. So a lot of these people, right, they have to provide certain domain-specific math functions that takes less area, but you have to freeze those areas. You don't have the flexibility. SambaNova freezes it to floating point 16 operators. So, I'm sorry, Cerebras freezes it to floating point 16. I don't know SambaNova, but I think they also have a fixed floating point 16 and a computation in a floating point 32 format. So it's predefined. So if the user says 8-bit is good enough, you just have to use whatever the hardware offers for you, whereas a GPU gives you, because they have software, they give you that flexibility to do maybe divide a multiplier into 2 halves. It's not as efficient because the multiplier grows as the square of the bits you want in the multiplier, but it's linear division if you want to divide it, right? So you lose some hardware efficiency, but you get that, right? So I was never a big fan of throwing a lot of silicon, but since the models are so big and you have to use so many different chips, then the question becomes, how do you integrate a lot of different chips and get your solution to work, right? So I've done a lot of math on GPU architectures, and one of the metrics I'd like to define is tokens per second per millimeter squared to say how efficient is your silicon.
Per millimeter squared, okay.
Right, yeah, per millimeter squared, right? Because at the end of the day, you can throw in the entire city of San Francisco and say, gee, I can do 1 billion tokens or something.
Yeah.
So, and then the other one is the tokens per watt. Right, because that at the end, these two metrics, you want the best of both worlds.
Yeah.
So I think we've run out of time.
Yeah.
So
Okay.
let me ask Sajat or Sam, anything else you guys want to say?
No, I think, thank you
Give
so
Raminda
much.
last-
I mean, it was so illuminating. I mean, the way you carried across, talked about different things, talked about about Cerebras, you talked about the LPUs, you talked about the reconfigurable RDUs. I think data flow units, sorry, RDUs. It was great. Thank you so much for coming in, and I think it was a great conversation.
It's my pleasure, and thank you for arranging this. And hopefully we'll have many more chances of discussing
We'll
hardware.
have to meet again at McDonald's on Sunday. I really enjoyed those conversations, right? And today was another one of those. So, hey, thank you guys all.
Thank you, Raminda. Thank you, everybody.
Thank you.
Bye-bye.